What we're talking about today is mainly section 1.2. I don't think we're going to get to 1.3. So what we're doing is we're looking at quantitative data with graphs. Quantitative is just numeric data. So we're going to talk about numeric data and the different graphs. Categorical, pretty much you need to know bar chart. Occasionally we use pie charts, but mostly we use bar charts. Numeric data, there's a lot more kinds of graphs. So some you might have seen before, some you might not have. We're going to talk about dot plots, stem plots, histograms. That's what all of that says. We're going to learn how to construct them. We're going to learn how to describe them. We're going to learn how to compare them. So if you go to this page of notes, please. Okay, when describing the distribution of a quantitative variable, what characters should be addressed? So one thing I want us to write real quick. When we're talking quantitative, another term for that is numeric. I don't love the term quantitative, so I will also say numeric. And specifically, we are looking at one variable only. So if we have one variable that is numeric, that we've described in a graph, what are we talking about? So in the homework that you guys just turned in, we talked about looking at the association. Talk about the most frequent category. Compare between the graphs, so on and so forth. That is a little wishy-washy for numeric variables. There's 4 things you're always going to address no matter what. You are always going to talk about C, S, S, U. The C stands for center. So where does the middle of the distribution look? You're not actually calculating it, you're just going to estimate it. 1S stands for shape, and we will look at some shape terms below. 1S stands for spread. And the U stands for unusual. Now, when I say unusual, I'm saying, are there any outliers? Is there a gap? Those are really the 2 main ones, but is there anything weird about it? The order doesn't matter. You just need to address those 4 things. We will do an example, but before we do, we have to talk about some shape terms first. Here are 4 different shape terms that you need to use or need to know. Symmetric, often something like that. This is also called bell-shaped. Now, single-peaked or unimodal. Unimodal just means one peak. Mode is peak. It's just a distribution that has one peak. So it could look like the one above. So this one that I've drawn in blue, we could refer to that as symmetric. We could say it's bell-shaped. We could say it's unimodal. Any of those will work. So I'm not going to draw a unimodal one. Skewed right is always where the tail is. So that right refers to the tail. So skewed left then has a long tail on the left. Now again, this is also unimodal, but the skew is very important. Now, people mess up the skew. It's not where most of the data is. It's where the tail goes. Bimodal, bi and mode is double peaked. So something like that is bimodal. And uniform has just the same distribution all the way across it. Okay, when you are looking at graphs, we are not concerned about what I'm going to call the little bumps. But instead, the overall shape. So we'll look at some examples. Okay, one thing that you do need to be able to tell me is if I give you a variable, you have to be able to tell me what shape you think it's going to follow. So if we were to look at the salaries of everyone that works in District 214. So if we were to look at the salaries of everyone that works in District 214, any idea what kind of shape those would follow? Any salary in general. So if you can think of like a pro basketball player too, if we looked at professional basketball players or professional baseball players, generally what shape are those salaries going to follow? What do you think? Skewed left. So skewed left would mean most people make money here and there's a few that make less. If you had to put in words what you think the salaries look like of the people that work in our district, what do you think?
Most of it's the same, but there's some that make more.
Okay, who makes more?
Like the superintendent.
Okay, if we look at the superintendent or anybody that works at the district office, they're going to make a lot of money, right? Okay, so maybe we could argue skewed right. Maybe we could argue symmetric. Does bimodal make sense? Probably not. Who else do we need to be concerned with? So we have a lot of people that make the similar amounts. Those are the teachers. We have the superintendent who makes a lot. Is there anybody else that is different from that? Custodians, the maintenance staff, some of the people who work part-time in the district. So this is generally how salaries are going to fall. Most people make around here. Some people make a lot. Can you come up with a variable that would be bimodal? So something numeric that you measure that's going to naturally fall into two groups. It relates to something in our classroom. So gender is categorical. What would the two?
I guess it's more like there's too many.
There's not too many. I just am not convinced that it naturally falls into two groups. That would be, it's possible. So if there was a class where most people got A's and most people got C's, that would be bimodal, sure.
Age.
Okay, what are your groups?
17,
It just seems like two bars then. What else could we measure in here? Height, maybe? Maybe height. Height, weight, things that come from the body tend to be symmetric. What about hair length? I would argue if we looked around the room, most people either have very long hair or short hair. You agree? So that's one that I would say would be bimodal. Is hair length. Okay, here's where that's going. Here's what we have here is called a dot plot of the 2004 season of the U.S. women's soccer team. There's the number of goals that the U.S. women scored in each game. So I would ask you, describe this distribution. I don't care about each individual game. I want to know, as a whole, what the distribution looks like. And so what we're going to talk about is, like we wrote above, we're going to talk about that CSSU. Again, the order doesn't matter. Just starting with some good vocabulary. The first thing that I'm going to do is write solely about context. So I'm going to say the distribution of number of goals scored during the 2004 U.S. women's soccer season is, so far that's just context. All I've said is context. Is it wordy? Yes, but I said everything that we were referring to. Remember, distribution just means it tells us the possible values and how often they occur. So if I'm going to look at the center is about the middle. Don't calculate it, don't waste your time. Guess where you think the middle is. So where you think like the mean would be. To me, the middle, the average looks like it might be about 3. Okay, so the soccer season is centered around 3 goals. Goals being the context. So then we're looking at shape. We're just trying to draw a shape in general. So if I went like this, there's a smidge bit of a dip here. We don't really care about that. So I don't care about these individual points in general. There's a bimodal shape. You don't need that long context in every sentence. Once is enough. So I'm going to say the distribution is bimodal with modes around 2 and 5. So far I've done center and shape. I still need to talk about spread. Spread is the variability. It's how wide the distribution is. So the distribution is spread from 0 to 8 goals. That is not enough for spread though. If we say 0 to 8, that's not a whole lot of information. That's only giving 2 observations. That's only looking at the lowest observation and the highest observation. So anytime you're talking about spread, you're going to tell me the lowest and highest. Also, where most of the data falls. So most of our data here is between 1 and 5, or even 1 and 3. So the spread is from 0 to 5 goals, with most games scoring 1 to 5 goals. And then last thing, is there anything unusual? There's no gaps. So a gap would happen if I took out these 3 games. That would be a gap. Or unusual observations. These are not unusual. They're pretty close to the 5. So if there was a game where they had scored 15 goals, that's pretty far away, we would say that's unusual. Because there's nothing unusual, I'm just going to say nothing unusual. Okay. Questions on that? Okay, other thing that you're going to have to be able to do is compare distributions. Compare. So right now, all we've done is describe a single distribution. If you are asked to compare 2 different distributions, 2 things you got to remember. The first thing is context, using variable names. Not just groups or units. And second thing you have to remember is you actually have to compare. So you are actually going to compare using explicit comparison terms. I need 5 more minutes of your time before we take a break. So we are going to compare the 2 dot plots below, and then we will take a 5-minute break. That work? Okay, so here we have 2 dot plots that we are comparing for the countries of the United Kingdom and South Africa, and it is household sizes. So if we just looked at a sample of families in the UK, and a sample of families in South Africa, here are their household sizes. If we're comparing, the first thing you're looking at is, this is numeric. Because it's numeric data, you're going to do CSSU. The same thing that we did above, but comparing. So for center, above we guessed the centers. So in this case, the center in South Africa is about 7. The center in the UK is about 5. You don't even need that. You don't need any numbers. All you have to do is compare. Which center is higher? South Africa. Yeah, center's about here. That's all you need. You don't need numbers. So I'm going to say the center of the distribution of household sizes in South Africa is higher. Than the center. I don't know what happened, guys. Oh, close. The center in the UK. Okay, that's the center part. If we do shape, what would we say the South Africa distribution is shaped like? If we just consider drawing over. Skewed right. Skewed right. Or if we consider these to be maybe unusual, if we ignore those 2 points. Maybe Bell, unimodal. So I'm going to say both countries have a unimodal shape. And then South Africa has a slight, is it a skew left or right? Right. You don't need to label that CSSU. I do. You don't need to. Makes you comfortable, great. Okay, spread. Again, I don't care about numbers. Veronica?
I was just gonna ask, so if it was like fully skewed right, would there be like a dot at every number?
Not necessarily every number, but there would be more than just 2. Spread. We don't need numbers. All we care about. Which distribution has a higher spread or more variability? South Africa. Yeah, the distribution for South Africa has a larger spread. And then unusual. UK has nothing unusual. We're going to say South Africa has 2 unusual observations. Observations is just the nice word for points. So 2 unusual points. Anytime points are unusual, you have to tell me why. So these 2 are unusual because their household sizes are much larger than the rest of the distribution. So there are 2 unusual observations with larger household sizes than the rest of the distribution. Okay, that is dot plots and CSSU. What we still have to do after the break is talk about 2 other graphs that we're going to learn how to construct. Interpreting them, though, exactly the same way. You already know how to do that. Questions for me before our break? Okay, so continuing. Next page, you have an example. I don't know if we have time for that, so we're just going to skip it. Anybody super upset? No, great. Let's keep going then. Okay, so we got 2 more graphs to talk about. One is called a stem plot. I would venture to guess you all have never seen these before, and then we're going to talk about histograms, which you definitely have. Okay, so what are the most important things when you are making a stem plot? You need labels, you need a scale, and you need a key. So we are going to construct a stem plot for the data below. A number of males and females were asked, how many shoes do you have? First thing we're going to focus on is just the female distribution. So we don't care about the number of shoes that males have. We're just going to look at females for right now. So what you're going to do is you're going to put what's called your stem. So there are numbers that are going to go in here, our stem, and then there are numbers that are going to go in our leaf. The stem is the starting number. So in our case, we have numbers in the 50s all the way down to the 10s. The first number only is what goes in the stem. So in our case, that's going to go 1, 2, 3, 4, 5. So our stem in this case is the 10s place, and our leaf, we're going to put the 1s place. So this is our key right here. And then you're just going to put all the numbers here. So if we're looking at all of the ones that are in the 10s, we have 13, 13, 13, 15, and 19. You're going to put them in numeric order. Since we already put the 1, what we need now is the 3. So we have a 13, another 13, another 13, and a 15, and a 19. You do not put commas. So it is understood that these are 5 different observations. 13, 13, 13, 15, 19. No commas. So then if we look in the 20s, we have 22, 23, 23, 24, 26, 26. So we have 22, 23, 23. And you're going to try to line up vertically so that it's easier to read. And then we have a 24, we have a 26, and a 26. Okay, so then looking in our 30s, we have 30, 31, 34, and 38. Okay, and then it looks like there's only one number in the 40s, and that's 49. And then in the 50s, we have 50, 50, 51, and 57. So this is our stem and leaf plot, or it's called a stem plot. We need a title, which I'm going to title it number of shoes. Okay, so if I were to ask you to describe this, it's kind of like the dot plot that we did before. So what I do normally, if I'm asked to describe this, is I take it, flip my iPad sideways so I can read it like a dot plot. So we would say the center is around maybe 25. What would we say the shape is? I would say bimodal, right? There's a peak here around the 20s and then there's a peak in the 50s. Our spread is from 13 to 57, so on and so forth. We'll describe again later if we have time, but I want to get through the construction part. Question on that? Okay. The reason people like stem and leaf plots is they're good for comparing. So I've drawn it this way for a reason. Females on one side, we're going to put males on the other side. So that's what we're going to do now. So we're going to have to put that label in. So these numbers in black represent the female distribution. The numbers on the left are going to represent the male. Now we're going to notice in the male, we have some numbers that are just singletons like this, that they don't have anything in the tens place. So we're actually going to need to add a 0 for those numbers. And you always read in, out. So our smallest number is 4. So we have 4, 5, 5, 5. So it's in, out. So we have 4, 5, 5, 5. We have 1, 6. And then we have 7, 7, 7, 7. So 7, 7, 7. Sorry that mine is kind of sloppy. And then we have an 8. Okay, so then we have 10, 10, 10, 10. So we have 10, 10, 10, 10. We have a 12. We have a 14. Oh, I missed an 11, didn't I? Oh well. Sorry, I missed an 11, so hopefully you can fix it easier than I can. And then we have a 22. And then we have 2 more, 35, 38. So now it's kind of like having 2 dot plots. You would then tip this one sideways also to look at the male distribution. Again, if we were comparing, we're doing CSSU. Female distribution has a higher center. The female distribution is bimodal. The male shape skewed, I agree. Where's the tail? Higher numbers or lower numbers? Skewed right towards the higher numbers, and so on and so forth. Questions for me? Okay, a few things you need to know. The first thing is you only want one number in the leaf. So you might have something like, we're looking at the number of pages in textbooks, right? And let's say that the number of pages go anywhere from 103 to 745. What you would generally do then is you would put the first number in the leaf and the stem rather. You would put the second number in the leaf, and then you just drop any other numbers. So I'm putting 1 and 0, the 3 doesn't matter. So anything else you have, you're just gonna drop it. Anybody know the term for that? It's not rounding, so we're not rounding, we're just cutting it off. Starts with a T. Truncate. So we are truncating. Okay, the other thing that you need to know is sometimes we will use what are called split stems. And what we do there, like if we took these stems right here and we split them, you would have a low and a high. A low and a high, and so on and so forth. Okay. The low is 0 to 4, and the high is 5 to 9. So for example, this 4 would go in the 0 low. The 5 through 8 would go in the 0 high. The 1 low would be the 0, well, I guess all of them. Okay. You don't do that a whole heck of a lot. You split when your data is clustered. So kind of like how it is here for the males. Their data is all kind of clustered together. So that would be a good place where you would split stems. It helps you see the shape better. Okay. How are we feeling? That, stem and leaf plots. Still got one more to go. Okay, questions for me on stem and leaf plots before we keep going? Yes.
If you were to do 0 low and 0 high, do you have to do that for each number inside the stem?
Great question. No. Generally, you do it for all of them, but you don't have to, no. Okay. Thank you guys for sticking with me. Let's look at this last example. This table has average points scored per game for 30 NBA teams in a recent season. So you can see the team and you can see the points scored per game. What you should be thinking when you see this is you should be thinking, this is numeric data. And then you should be thinking, I only have one variable. We don't care about the team name. All we care about is this points scored per game. So if we have one variable and it's numeric, our options are we can make a dot plot, we can make a stem and leaf plot, or this new one is called a histogram. I'm not going to have us make a dot plot. Do you think if I did that you would be fine putting dots for all of the teams? Right? Like there's no reason we need to do it now. We are going to make a histogram though. Histogram, this is a new one. Have you guys heard that term before? Some of you maybe. Okay, a histogram is like a bar chart, but it's for numeric data. So we're going to have to take these points scored per game and we're going to have to put them into what we call intervals. So we need the points scored per game, and then we need the frequency. It looks like the lowest points scored per game is 93.2, and the highest is 106. Okay, a lot of times if you are asked for a histogram, you will be given the intervals. So you will be told, go from 93 to 95, so on and so forth. I didn't tell you that here, so we're going to have to come up with them on our own. So let's say that we're going to go from 92 to 108, just to give us a little bit of extra room on the sides. So that is 16 wide. So maybe we do 4 intervals. So let's go from 92 to 96. And then we're going to go from 96 to 100. And then we're going to go from 100 to 104. And then we're going to go from 104 to 108. Now, I have this written a little bit poorly. This means just before 96. So this is 92 to just before 96. So first thing we're going to do is count how many teams fall into that category. 92 to just before 96. So I think there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 96 to 100 would be 1, 2, 3, 4, 5, 6, 7, 8 would be 8. 100 to 104 is 1, 2, 3, 4, 5, 6, 7, 8. And then 104 to 108 is 3. Now we're told there's 30 NBA teams, so maybe add those up and make sure that they get to 38, or to 30 rather, I think they do. Okay so far? Okay, so then there's 2 things you can do with this histogram. You can use frequency or relative frequency, whichever one you want. Because I didn't tell you, you can pick. I'm going to pick frequency because I'm lazy and I don't want to have to calculate relative frequency. So, x-axis represents the points scored per game. And then y-axis is frequency. I'm going to put a title like NBA team scores. Okay, frequency has to start at 0. The y-axis has to start at 0. The x-axis doesn't matter. So for the y-axis, I'm going to go from 0, 5, 10, 15. What I saw some of you do on your graphs before is you only labeled these numbers. You should not be just randomly marking those. You should be scaling and then choosing appropriately. And then we're going from 92 to 108. So I'm going to call this 92, 96, 100, 104, 108. Okay, so then our first one, 92 to 96 has 11 in it. 96 to 100 has 8. 100 to 104 also has 8. 104 to 108 has 3. Hopefully your graph looks a lot better than mine. It does not look as slanted as mine does. Okay, how do you know, looking at this, that it's a histogram and not a bar chart? Okay, do you remember talking about the bar chart? There should be spaces in between. This has got no spaces. Okay, so then to read this, this is all the numbers between 92 up to 96. Okay, what I want you to do with the person next to you right now is describe this. So describe the distribution of points scored per game for these 30 NBA teams. Turn to the person next to you and then we'll come back together in 2 minutes. I know you didn't have a ton of time. Let's just talk about it though. What did we say for context? How did we start out? Or if we had actually written it out, what would we have written? Okay. Should be something like the distribution of points scored per game for 30 NBA teams in a recent season is center. Where do we say the center is? About 98. Great. Shape? Skewed right. The spread, I would say, the spread is from 93 to 106 points. What else did we say though? Hopefully where most of the data falls. So 93 to 106 with most of the data between 93 and 102. And then there's nothing unusual. Okay, I cannot stress enough that your context needs to be strong. So, distribution of points scored per game for the 30 NBA teams. As long as you write it once, that's enough. We're going to write down one more thing and then we're done. Okay. Okay. Last thing you need to know. We're not going to do all of these. Why would we sometimes prefer to use relative frequency? Think back to a bar chart. When did I say you have to use relative frequency compared to frequency? Veronica? If you are comparing two samples or distributions. And it's because they often have different sample sizes. Anytime you have two different sample sizes, you're going to have to use relative frequency.